In this next section of Chapter 20, we're going to talk about motional EMF and generators. So basically the uses for this generation of an EMF due to a changing magnetic flux. One application of a magnetic flux is this motional EMF, and this is basically another way to come at how we're going to generate a current with a changing magnetic field. Or magnetic flux, really. So here we have a bar that is made of charges. There are charges in the bar, and the bar is moving to the right in a magnetic field. So to figure out what's going to happen, we're going to use our right-hand rule again, that the magnetic field in this particular picture is pointed into the page. So I'm going to point my fingers into the page. The velocity is to the right, so I'm going to point my thumb to the right. And then the force on any positive charges is going to be up. So if I have a positive charge, which would be my current, so if I have a positive charge in here, the force is up. So that means the force on any electrons is going to be down, going in the opposite direction of the force on a positive charge. And that magnitude of the force is from our QVB. So this end will tend to become positively charged because positive ions move up, and this end of the bar will become negatively charged because the negative species will move down. So there'll be a potential difference across this bar. The value for the potential difference is found using these formula. So we know delta V is equal to E times D, and we know that delta V is also equal to VLV. So we're going to use this form more often in this case, but we remember delta V is equal to E times D. And since we're talking about L, that D becomes an L in the case of this bar, because we want to know the potential difference across the bar. So delta V is equal to VLV, where the upper end is at a higher potential than the lower end. If if the bar moves in the other direction, then the charge is going to reverse as well. So if we attach this bar to a couple rails, and so that it maintains contact, we do know that the bar becomes charged at the end, and that will set up a current. So this is another way to generate current, is to be able to move this bar in a magnetic field. So what is the math for that? So we know that Faraday's law for EMF is E is equal to our change in magnetic flux. Our change in magnetic flux is equal to basically our change in area. This is constant. And that means that the magnetic flux could be increasing or decreasing because there are more lines, not because it's getting stronger or weaker. Then we separate out the area into a length by distance. And if we pull out L, that this length is not changing, then we have dx dt, and guess what? Dx dt is in fact velocity. So Faraday's law is where this rule really comes from. So the EMF generated is equal to BLV, and if we wanted to find the current, we just use Ohm's law, this being our EMF, our voltage, divided by resistance to get our current. Now we're going to go back to Lenz's law and see what Lenz's law gives us for an answer for the direction of the current. Remembering that Lenz's law says that any induced current must oppose the change in magnetic flux. In this first case, we have the bars moving to the right. That means the flux is increasing because my area is increasing. And that means the ring is basically going to say, so B is constant, but A is increasing, that the magnetic field is into the screen and the magnetic flux is increasing into the screen. And the induced magnetic field will want to oppose that change. So since it's enclosing more and more magnetic field lines, because the area is getting bigger, it's going to want to oppose that change by making a magnetic field in the opposite direction. It says, I had 5 magnetic field lines and you're giving me more. I don't take more. I am happy with what I have. I don't change. And so it's going to create magnetic field lines in the opposite direction. In this case, the magnetic field lines are coming out towards you. So grab your ring and put your hand through the magnetic field line towards you, and that will tell you the direction of the current with your thumb. So on the right side here, my thumb is pointed up, so my current is going up, and if I rotate my hand all the way around, I can see that the current is in fact traveling in a clockwise direction, so going all the way around in a clockwise direction. Now if I reverse that direction, and now the magnetic field lines are still going in, but my velocity is to the left, that means we're going to want to recover that magnetic flux. Is the area is decreasing, so my flux is decreasing with time, and so we want to recover that. So the loop says, I had 10 magnetic field lines and you are taking them away, so I'm going to make my own so I can have 10 magnetic field lines. So we're going to put more magnetic field lines in. Here the magnetic field lines are in to the screen, so I'm going to put my hand in, and we'll find that the current this time is in a clockwise direction. It's indicated by that arrow. We can also look at this from a conservation of energy point of view. Assume if we're moving the bar to the right, that the current actually goes in the other direction. That means the induced current would be clockwise, which isn't right, but we're just going to assume that it's clockwise for this argument. Then the force, the induced force on this would be the other direction and pushing it and making it go faster and faster. And because it won't want to oppose the change. So it's going to say instead, I like the change, let's keep going. Then we're going to get an acceleration of the system with no expenditure of energy, which simply cannot happen. So that's another way you can sort of think about the direction of the current, that it must be opposing the change. Okay, now for a little bit of mathematics, we're going to use this BLV formula to determine the current and the resistance of this particular situation. So an LED light can be illuminated with as little as just 2 volts of a potential difference across it, and then it would take 30 milliamps of current. If we're going to use the hand generator to power the LED, how fast must we move our hand to provide sufficient power to generate enough current to make this thing go? So the voltage is equal to E over BL, just using this formula, and that's equal to 2 volts over 1.6 Teslas. So it says that's the magnetic field, and 0.25 meters, which gives us 5 meters per second to be able to generate that voltage. And who can resist an opportunity to use Ohm's law whenever we can? So we're going to figure out the resistance of this particular LED. The LEDs don't have a resistance in the typical sense, but they still have a voltage drop associated with a current. So this particular LED, we would say, would be 66.7 ohms. So there's your numbers. And now you give Lenz's law a try and try to figure out what direction the current is going when we're moving the bar to the right. Okay, hopefully you've had a time to think about it. So here my area is increasing because I'm moving the bar to the right. So that means my magnetic flux is increasing. And so the induced magnetic field will want to oppose that change. And to oppose that change with the magnetic field going in, I have to generate a magnetic field coming out. And again, if I use my loop, then I want to have it come out towards me. Then the current needs to be to the left in order to oppose that change.